Alright, hey guys, we'll be going over the extended response in IMV Exam 2 2024 today. So let's get into it. Alright, so question 1, f of x is defined as this function. Find the tangent of f of x at the point A in terms of A. Alright, so the first thing you should always do in the extended response question is as soon as you have, as soon as they give you a function, you just define it on your CAS immediately. So we're going to define f of x as x minus 1 squared times x plus 1 squared. Right, and we want to find the tangent line of f of x at x equals a, and we get this. So the answer is, whoop, that's too thick. The answer is y equals 4a squared minus 1x minus a squared minus 1, 3a squared plus 1. There we go. Next question, find the values of a for which the tangent only has one intersection with f of x. So what we're going to do here is we're going to solve, and we're going to set f of x equal to this tangent. And we get 3 solutions. Now, this last one here, x equals a, is always defined, no matter what a is. However, these ones in the square roots obviously are only defined when this inside function is greater than 0. So when it's less than 0, we're only going to have one solution. So when a is less than -1, or when a is greater than 1, we'll only have one solution. Find an expression for the area bounded between f of x and the line y equals a in terms of a. All right, so let's go on Desmos to visualize this. X plus 1 squared, and then the line y equals a. So I'm going to try and find this area here. Okay, so first we need to find the intersection points. And to do that, we're just going to solve, and we're going to let a equal to f of x. And we get that x is equal to these 4 solutions. However, the question states that a is greater than or equal to 1. Therefore, these first 2 solutions here will be undefined. So we're only looking at these 2 solutions, these last 2. So the area is equal to the integral from negative square root a plus 1 over root a plus 1 of the top function minus the bottom function, which gives us negative square root a plus 1 square root a plus 1 a minus f of x dx. Yeah, so it just gives us that. And yeah, so you just type that in, or not type that in, you'd write that in for your answer. But I'm not going to do that, so it just takes too much time. Alright, next question. The normal to f of x at b, where b is between 0 and 1, intersects twice. Find the minimum bounded area. Alright, so for this question, I tried a lot of things, and I wasn't able to find the exact answer. However, I was able to find an approximate answer. So if I am able to find an exact answer for this question, then I'll place it in the comments, and you guys can also, if you guys also found an exact answer, please tell me as well. All right, so what we're going to do here is we're going to, so normal line at f of x, x equals b, and we're going to create a graph f of x, and also create a slider with the variable b between 0 and 1. Okay, and then we're going to copy and paste this normal line Did I copy it? Okay, I did. And we're just going to try and find, this small area bounded between both of them. So we're going to go menu, analyze graph, bounded area from one intersection point to the next. And then let's slide B and see where it goes. So as you can see, basically from point 8 all the way to 0, the graph is increasing infinitely. So the minimum has to be between 0.8 and 1. So let's adjust that. Now let's keep going. So it's decreasing, 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 and it's actually increased between 0.88 and 0.9. Therefore, the minimum must be in between those two. 0.9, 0.88, and we're probably going to need more decimal places here. So let's change the float 7. All right, so now let's see what we have. So from 0.88, it decreases and then decreases again. But then from 0.884 to 0.886, as you can see, it increases. So the solution is somewhere between 0.884 and 0.886. However, we can already approximate now to 4 decimal places, and we can say that the approximate area is 0.0877. So approximately 0.0877. So, what you would usually do is you would find these two intersection points in terms of B, and then find the area in terms of B, and then minimize the area, obviously. But I found that when I try to do that, the CAS is a little bit, it explodes to a million pieces, and it doesn't work. So, yeah, if you guys have any other ways of finding the minimum area, please tell me. But other than that, we're just going to settle with the approximate value. All right, next question. Find the sequence of transformations that transforms this function into f of x. So what we're going to do is we're going to let g of x equal to x squared minus 4 squared. And when we graph this, right, x squared minus 4 squared, you can see that the turning point at x equals 0, it doesn't actually change. It stays at x equals 0. So what we can conclude from that is that there are no translations within the transformation. There are only dilations. So this means that in order to go from g of x to f of x, g of x must have undergone some dilations, which we'll call a times g of c of x. And this will be equal to f of x, which means that f of x minus a g of b, or not b, sorry, c of x is equal to 0. And so let's expand that expression. So first of all, define g of x equals squared minus 4 squared, and then expand f of x minus a times g of c of x. And we get this. And as we said here, that has to equal to 0. And the way that can equal to 0 is if the coefficient of x to the power of 4, the coefficient of x to the power of 2, and the constant term at the end are all equal to 0. So if we look at the constant term at the end, negative 16a plus 1, this has to equal to 0, which implies that a is equal to 1 over 16. And then when we look at the coefficients for x to the power of 4, which is negative a c to the power of 4 plus 1, this also has to equal to 0. But then again, a is 1 over 16, so this becomes negative c to the power of 4 on 16 plus 1 is equal to 0, which means that c is equal to 2. So therefore, our transformations are a dilation of factor 1 on 16 from the x-axis, and then a dilation of factor, so C is 2, so 1 over 2 from the y-axis. There we go. All right, next question. F of x plus c can be expressed in the form of that. Find the values of I, j, k, and c. All right. So we can use a similar method here. What we can do is we can let f of x plus c equal to this. Therefore, f of x plus c minus this is equal to 0. So let's do that. Expand f of x plus c minus x minus I squared x minus j x minus x plus k, and we get this. And as it, once again, the coefficients of x cubed, x squared, x, and the constant term all have to equal to 0. So what we're going to do is we're going to go menu 3, 7, 1. We're trying to solve for 4 different variables, and those are c, I, j, and k. So if we look at the x cubed, we need 2i plus j minus k to equal to 0. And then when you look at the x squared, we need negative I squared minus 2 times I times j plus 2 times I times k plus j times k minus 2 to equal to 0. And then the coefficients of x is going to be I squared times j minus I squared times k minus 2 times I times j times k. And that's it. That's going to equal to 0. And then finally the constant term c plus I squared times j times k plus 1 is equal to 0. Enter. So we get a bunch of solutions, but as the question said, j and k both have to be greater than 0. So obviously we're going to ignore this one. And then we're going to not ignore this one, because here they're both greater than 0. So this solution states that c is equal to -1, I is equal to 0, and j is equal to k is equal to √2. And that's it. All right, question 2. Let f of x equal tan of the natural log of x. So I'm just going to make a new file. Then once again, define. There we go. All right, so f1 with the domain of p to q is defined such that p to q represents the maximal domain. Okay, so find all possible values of p and q. All right, so let's look here. Let's look at what tan of ln of x looks like. And as you can see, p and q are going to be each of the asymptotes. So for example, if p was this asymptote here and q was this asymptote here, then that would create one set of values where f1 of x has an inverse, or when it's 1 to 1. And then, there's also other ones. There's from here to here, and then it goes on to infinity. And then also, when we zoom in here, there's actually smaller ones, which also have, their own. So how do we find these asymptotes? Well, tan of ln x has a denominator of cos, So cos of ln x is equal to 0, which implies that ln x is equal to pi on 2 plus pi n, which means that x is equal to e to the pi on 2 plus pi n is an integer. So what we can say is that if p is equal to e to the pi on 2 plus pi n, then q is going to be the next asymptote to the right of that, which is when n is equal to n plus 1. Right, so the next asymptote. And yeah, that's it. So n is equal to z. And yeah, that's it. That should be the answer. Just trying to check something. Yeah, it should be fine. Yep, okay. So those are the all of the asymptotes essentially in a general form. Find a general rule for f of -1 of x, the inverse function of f of x. Okay, so what was I doing? Oh yeah, x is equal to tan of ln y, which means that ln of y is equal to arctan of x plus pi n. N is an integer. And then y is equal to e to the arctan of x plus pi n. And n depends on which domain we're talking about, so you know what value of n is here. So that's equal to f -1. Find the equation of a tangent f of x at every x-intercept. Okay, so what is every x-intercept? That's when the numerator of tan of x is equal to 0. So sine of ln x is equal to 0. You know what? Actually, no, I'll do the calculation here. Is equal to 0, which means that ln of x is equal to pi n, which means that x is equal to e to the pi n. And then we're just going to put into the cas tangent line f of x equals e to the power of pi times n. And we get this. Now here, the cas is assuming that n is a real number. However, we can assume that n is an integer, right? N is an integer. And what that means is that cos of n pi, where n is an integer, is going to be either 1 or -1. And then if we square it, well, then it's always going to be 1. And then same thing with here. Sine of an integer times pi is going to be 0, and then this is going to be 1. So what it's going to look like is y is equal to e to the negative pi n x minus 1. All right. Now find the x-intercepts of the tangent found in I in the form of a general solution. Okay, so pretty simple. Solve e to the power of negative pi times n, x minus 1 equals 0. X is equal to e to the n pi. Pi n 0. N integer. All right, find the sequence of transformations that transforms one tangent found in I to another unique tangent found in I. State your answer as a general solution. Okay, so what do we have here? We have y is equal to e to the negative pi n x minus 1. And remember, n is an integer, so what we can do is that if we want to take it to any other integer, if we want to take n to another integer, which we'll call, I don't know, b, then we need to add or another integer to it to get to b, right? So another unique tangent would be n plus k x minus 1, which is equal to e to the negative pi n multiplied by e to the negative pi k just using exponential laws, x minus 1. So as you can see, from here to here, there has been a dilation of factor e to the pi k from the y-axis, where k is integer. All right, so now we have, now it's given us a domain, g of x equals f of x. Find the bounded area between g of x, its inverse, the x-axis, and the y-axis, corrected 2 decimal places. All right, so let's just write that up. So what does it say? E to the negative pi on 2, negative pi on 2, x e to the pi on 2. So that one. And then the inverse of that is going to be e to the arctan of x. So we're going to find essentially this area in between them. And in order to do that, we need to find this intersection point. But since it's just giving us 2 decimal places, we can just use an approximate value, which is 3.69259. So the area is going to be integral from 0 to 3.65259 of the top function, which is e to the arctan of x, minus the bottom function, which is integral from 1 to 3.65259 of tan of ln x, which is approximately 3.65259 e to the arctan x minus 3.65259 tan of ln x. 6.38, 6.2 decimal places, yep, 6.38 units squared. All right, g of x is translated c units up. What is the maximum amount of intersections between the translated function and its inverse? What's g of x? Oh, this, okay. So what we can do here, c units up, that just means c, add slider. And then that changes the inverse to arctan of x minus c, like that. So when we slide around C, we can see that the maximum amount of intersections is 3. So 1, 2, 3. And then as we increase C, it goes from 1 to 2, and then stays at 1. So 3. 3. Find the values of C to 2 decimal places for which the translated function of g intersects with its inverse at the maximum amount of times found in f. All right. So I'm going to define g of x as f of x plus c. Now, when we do this, we can see that there is a point where they have 2 points of intersection. So one here, and then, they're tangential to each other at this point. And then when we decrease c again, they have 3 intersection points, and then they're tangential again, down here this time. So I want to find, well, when are they tangential like that? And what we can do is we can realize that they're tangential to y equals x. So what I'm going to do is I'm going to find the tangent line of g of x, which is f of x plus c, at some point, at any point x equals a. And yeah, we get that. And then what I'm going to do is I'm going to see, well, essentially, when is this equal to y equals x. So menu 3, menu 371, solving for a and c. So the gradient has to equal 1, therefore a cos of ln of a squared equals 1, and then the x-intercept, the y-intercept, sorry, has to equal 0. Oh, what do you mean about multiply? This. There we go. So a is equal to 1, c is equal to 1, or a is equal to 2.3767, and c is equal to 1.2 blah, blah, blah. And we're going to ignore these ones because we're going to ignore this one because I actually don't know where that solution came from, actually. Is there another place where it's tangential? That's one. That's weird. That solution just came out of nowhere. So let's just ignore those. So 1.20164, or when c is equal to 1. Now, just give me a second here, because the CAS software gives this in decimal places, but I'm pretty sure the handheld CAS gives it in exact values. So let me just do that. So just bear with me a second. You guys can skip the video until I find the answer. Almost done. That is so hard to work with. All right, should be. Oh, okay, so it seems like the CAS does not give an exact answer as well. Ah, damn it. Does it say give it to 2 decimal places? Oh, it does. Oh my god, I'm so stupid. All right. So the values in which there are 3 intersections is when c is between 1 and 1.20. Oh my god, that was so stupid. All right. C is between 1 and 1.20. Okay, that was a waste of a few minutes, but let's move on. All right, question 3. Company manufactures 2 types of batteries. Did I miss anything? No. 2 types of batteries, A and B. They produce 50% more A batteries than B batteries. The company claims, okay, a bunch of information. So here we can say that A is normally distributed with a mean of 400 and a standard deviation of 50. And then B is normally distributed with a mean of 500 and a standard deviation of 60. If a battery lasts for under 75% of its mean duration, is labeled defective. Calculate the probability that a randomly selected type A battery is effective. So we need to find what's 75% of 400. 300. Therefore, if the battery is less than 300, then it's defective. So we're going to go menu 552, lower bound negative infinity, upper bound 300, 400, and then 50. Was it 50? Yep. So 0.02275. 0.0228 to 4 decimal places. And then same thing for B. So 500 times 0.75, so 375. And a standard deviation of 60, mean of 500. and it was 375. 0.0186. There we go. A randomly chosen battery is found to be defective. What is the probability that is a type A battery? All right, so this is a conditional probability. So probability A given defective is equal to probability A and defective over probability defective. All right, to find this out, we need to look at the information where it says 50% more type A batteries than type B. So if there were, for example, 100 type B batteries, 50% more than that is going to be 150 type A batteries. This means that 60% of the batteries are type A and 40% are type B. So the probability that we choose a type A battery is 3 on 5, and the probability that we choose type B is 2 on 5. So probability of A and defective is going to be 3 on 5 multiplied by our answer to A, so 0.0228. And the probability that it's defective is the probability that it's B and defective plus the probability that it's A and defective. So B and defective is going to be 2 on 5 times our answer to the previous question, 0.0186, and then plus 3 on 5, 0.0228. And that gives us, so 0.6 times this over, let me just put that there, and then this over and plus 0.4 times U. So that gives us 0.6471. And what's the, okay, I'm guessing 4 decimal places, 0.6471. There we go. Okay. Find the minimum number of batteries to be packed into each box so that the probability that at most 2 batteries are defective is 0.9. So for this question, I'm going to assume that each box also follows the same rule that there are 50% more type A batteries than B batteries in the box. So this is going to be a binomial. X is binomial with a number of trials of n. We don't know what n is, and the probability of success is the probability that a randomly selected battery is defective, which we found to be this. So let's see what that is. In the denominator here, 0.021094. 0.021094. Okay, so probability that at most 2 batteries are defective. So probability that x is less than or equal to 2. So this x equals 1 plus probability x equals 2. So this is going to be equal to, I don't know if we can put that into the, no, I don't think we can. Okay, so this is going to be 1 minus this, 0.9789, 0.9789 to the power of n, plus n plus 0.021094, n multiplied by 0.9789 to the power of n minus 1. What was it? Yeah, n minus 1 plus n choose 2 times 0.021094 squared, 0.9789 to the power of n minus minus 2. And we want this to be 0.9 equal to 0.9. All right, so what I'm going to do is I'm just going to enter this here. And then what I'm going to do is I'm going to go 1 minus n's to the power of n plus n's times n times 1 minus n's to the power of n minus 1 plus n choose 2, which will go menu 5, 3 n 2 times n's squared times 1 minus n's to the power of n minus 2. And we're going to solve and let this equal 2.9. Hopefully, oh, it does, thank God. All right, so n equals 52.7. And it says the minimum number, so we're going to have to round up. So we get that n equals 58 boxes. So the probability that at most 2 batteries are defective is 0.9. Yes, I think so. Should we round down or round up? I think it's round down. Round up, sorry. Yeah, round up. 58. Okay, how many boxes may be packed until it is less than 10% certain that a box contains no defective batteries? Okay, so no defective batteries means 1 minus this, 0.9879 to the power of n is equal to 0.1. So let's once again copy this, solve 1 minus n's to the power of n is equal to 0.1. So 108 boxes may be packed. 108 boxes may be packed until it is less than 10% certain. A worker is sorting out the company inventory. It comes across 2 unlabeled boxes. They know that one is A, one is B. The worker tests one battery and labels the box as type A. If the battery lasts less than 425, find the probability that the mislabeled boxes. Okay, so to do this, we need to consider all situations. So he can make a mistake if the box he chooses is type A, but then he decides that it's B, or if the box he chooses is B, but then he decides that it's A. So A, but then he decides that it's B. So what is the probability that we choose the A box? Well, that's just a half. And then what's the probability that he decides that it's B? Is if the battery lasts more than 424 hours. So probability that A is greater than 425. And then plus probability that the box is B is a half. And the probability that he decides it's A is B if it's less than 425. So this is going to be menu 553, not 3, sorry, 552. 552. Lower bound is infinity. Nope. Lower bound is 425. Upper bound is infinity. And then we're doing A, so the mean is 500. No, 400 and then 50. Yep, 400. 450. So that's that one. And then we're going to do the other one as well. So menu 552, less than 425, 500, and then 60. And then we're going to add these two together and then divide by 2 because of the half. And this gives us how many decimal places? 6. Oh, let's just put that down there. 207094. 207094. There we go. All right. Guys, once again, I need a pee, so I'll be back. Can't hold it in anymore. BRB. Alright, I'm back. This time I actually edited the video, so yeah, it's all good. Alright, question 4. Let there be functions f of x equals... Alright, immediately start a new document. Define our functions. Define f of x is equal to 3x. Then define g of x is equal to pi minus 3x sine of 3x. Alright, find the sequence of transformations that maps f onto g. How are we going to do this? It's kind of hard to just look at it and be like, because your first thought may be, okay, so maybe it's like reflect in the y-axis to make this x negative, and then maybe, translate pi on 3 to the right for this pi. But then remember that you also have to apply it to this x, so it may not work out as you think. So what we're going to do is just going to graph these two. 3x sine of 3x, and then pi minus 3x sine 3x. Oh, and as you can see, it is literally just a translation of precisely pi on 3 to the right. So translation pi on 3 units right. And we can check this by going minus pi on 3 minus pi on 3. And as you can see, they line up perfectly. Yeah, so let's go. Find the area bounded between f of x and g of x between x equals 0 and x equals pi on 6. Okay, so let's get rid of these. Okay, so x equals 0 to x equals pi on 6. That's probably this point. Yep, so just this area here. So it's going to be integral from 0 to pi on 6 of the top function, which is g of x. Where is it, g of x? Yeah, it's g of x. Minus f of x, which gives us 0 to pi on 6. Pi minus 2 on 3. Pi minus 2 on 3 unit squared. H of x is the quotient of the functions f of x and g of x. Find the rule for h of x. Okay, that's pretty easy. So we're going to define h of x to equal f of x over g of x, and then h of x is equal to 3x over pi minus 3x. 3x over pi minus 3x. Find the domain and range of h of x. Okay, so now this is a tricky one because you guys may think that, okay, we can just find the domain and range of this. However, remember, it's a quotient. So even if it's defined here, even if a value of x is defined here, if it's not defined here at g of x, the function is still going to have a gap there. It's going to like have a little hole. So domain, if we let g of x equal to 0, not define, solve, g of x is equal to 0, we get x is equal to a multiple of pi on 3. So the domain is R except pi n on 3, where n is an integer. Yeah, so if it's any of those values, the denominator will be 0 and it won't be defined there. And then also the range, obviously since we can't substitute any of these in, if we go h of, if we substitute, let's just copy this, x equals n times pi on 3, we get this. So what this means is that the range, the y values, can't equal any of these. So y are, where n is n over 1 minus n, where n is an integer that is not 1. So if we just graph what that may look like, so it's just like a normal hyperbola, but what it will really look like is that at pi on 3, 2 pi on 3, 3 pi on 3, there should be small holes in the function where it's empty. All right. And one more thing. Let me just check something. Should be pi on 3, and then this asymptote should be at -1. I assume. Yes. Let me just check something real quick. And yeah. So since this over here does not account for the asymptote at y equals -1, then what this really is, it accounts for all the holes made by this domain, but it does not account for the asymptote at -1. So we're just going to do this. And yeah, this you guys remember, you guys can correct me if I do anything wrong, but yeah, I'm pretty sure that's the answer. All right, so now h1 of x, same function, but just from pi to infinity, show that h1 of x is strictly increasing. All right, so to show that something is strictly increasing, we have to show that if x1 is greater than x2, then h of x1 is greater than h of x2. That's the definition of strictly increasing. All right, so what we're going to do is we're going to let x1, x2, and x1, x2 domain of h1 there in the domain of h1. So this implies that -3x1 is less than -3x2, right? We're multiplying it by negative, so the sign is going to flip. And then we can add both sides, pi. That. And then from here, we can flip a fraction. So 1 over pi minus 3x1, then 1 over pi minus 3x2. And the sign also flips. And the reason this is because pi minus 3x1 is less than 0. Why? Because we've said that x1 and x2 are in the domain of h1, which means that they're greater than pi. So if x1 here is greater than pi, well then pi minus 3 times x1 is going to be less than 0. Same with x2. So that's why we can change the sign. And then therefore 3, what was it? What's the function? 3x over pi minus 3x. So before that, what I'm going to do, expand I'm just going to say quickly here, is equal to that, just a different form. So this implies obviously multiplying both sides by pi. and then minusing 1 from both sides, which implies that h1 of x1 is greater than h1 of x2. And yeah, so we've showed that if x1 is greater than x2, then h1 of x1 is greater than h1 of x2. Therefore, strictly increasing. All right, last question, for question 4 at least. Let P of x equal x sine of x and Q of x equal x cos of x. P of x and Q of x have infinitely many positive intersections. Find the area bounded between P of x, Q of x, the line x equals 2n, and the line x equals 2n plus 1. Okay, so what do we do here? X equals 2n, that's all the even numbered solutions. So that's essentially 5 pi on 4, and then 5 pi on 4, the next one will be 13 pi on 4, and 21 pi on 4, and so on. So x2, x of 2n, is equal to 5 pi on 4 plus 2 pi n. 2 pi... no, 2 pi n minus 1. Because the reason being, when n is equal to 1, then x of 2n is equal to 5 pi on 4. So we need this to equal to x of 5n. That means that x of 2n plus 1, which is the next solution after 5 pi on 4 plus 2 pi n minus 1. 5 pi on 4 plus 2 pi n minus 1. And then if we just look at the graphs real quick, you can see that every single intersection point is pi away from each other. So 7 pi, 9 pi on 4, 13 pi on 4 are all pi away from each other. So the solution next to x of 2n is going to be x of 2n plus pi. All right, and then the area is going to just be equal to the integral from 5 pi on 4 plus 2 pi n minus 1 to 5 pi on 4 plus 2 pi n minus 1 plus pi of the top function, which is always going to be x cos of x and the reason that is because even though x sine of x is sometimes the top function, that's only when the point of intersection is the left point of intersection is x of 2n plus 1, but this is the right point of intersection, so the x cos of x will be the top function, and this is equal to menu for 3. What was it, bro? Right. 5 pi on 4 plus 2 pi n minus 1, and then this plus pi of x cos of x minus x sine of x, which gives us this. And then what we're looking at here is, once again, the CAS isn't assuming that n is an integer, but we can. So if n is an integer, well then this is just going to be equal to cos of pi on 4, which is root 2 on 2. And then same with the sine over here. This is also going to be equal to root 2 on 2. So let's change that. times square root 2 on 2, and change this, square root 2 on 2, which gives us this. Root 2 pi 8n+1 over 2. And there we have it. Yeah, so we can check it. We can check if it's correct. So when n equals 1, which is when x of 2n is equal to 5 pound 4, then this is going to be equal to 7 pi root 3, 7 pi root 2 on 2. And then if we want to find it using just normal integration, it's going to be 5 pound 4 to 9 pound 4, which is also 7 root 2 on 2. So yeah, that is the answer. Okay. Yep, cool. Now I'm just thinking here, we haven't actually taken into account this small area here. So what I'm going to do is I'm going to check something. Fuck, my voice is so croaky. Right. 0 to 5 pi on, sorry, pi on 4. Pi root 2 and 4 minus 1. And if we do multiples. Interesting. I can't be bothered doing the rest, but yeah, that is the solution for that. Moving on, question 5. F of x equals a times e to the bx, where a and b are positive numbers. Find the equation of the tangent and normal to f of x at x equals 0 in terms of a and b. All right, so let's create a new file. Add calculator. Fine. Whoa, I'm not that excited. Define f of x is equal to a times e to the bx. This e. Oh my god. To the bx. And we need to find the tangent line at x equals 0. So tangent line is y equals a bx plus a, and the normal line is a or y equals negative 1 over a bx plus a. Yeah. Find the x-intercepts of the tangent and the normal in terms of a and b. Okay, so that's pretty easy. We're just going to solve. Set this equal to 0. We get that it's negative 1 over b for the tangent. And then this one is a squared b. The tangent and normal form a triangle with the x-axis. Find the area of this triangle. Okay. So what this is going to look like is this is negative 1 over b, and this is a squared b, and this point is f of x when x equals 0, and when it's equal to 0, the y coordinate is a. So this is a, and we need to find this triangle. All right, how do we do that? Half base times height. So area is equal to half times the height, which is a, so a on 2, multiplied by the base, which is a squared b plus 1 over b. There we go. Fully define the inverse of f of x. Okay, so f negative 1, the range of, sorry, the range? yeah, the range of f of x is 0 to infinity, so the domain of the inverse is going to be 0 to infinity. And the function is going to be equal to, so literally just rearranging this, so a e to the b y is equal to x, we'll get that y is equal to 1 over b ln x on a. There we go. Find the values of a in terms of b such that f of x is tangential to its inverse at their single point of intersection. Okay, so what is that going to look like? A times e to the bx and 1 over b ln x on a. So what that's going to look like is that somewhere around here, like that, they're going to be tangential to each other. And what that also means is that they will have a tangent at y equals x, as you can see. So we need to find when f of x has a tangent of y equals x. So what we're going to do is we're going to go tangent line f of x at some point c, which is unimportant. Let's add a voice crack. And we need to see when this is equal to the line of y equals x. So when is the gradient equal to 1, and when is the y-intercept equal to 0? So how are we going to do that? We're going to go menu, 3, 7, 1. Solve for two variables, a and b. We're going to go a times b. I'll just copy it. This should be equal to 1, and this is equal to 0. And we get this. So a is equal to c over e, and b is equal to 1 over c. But we wanted a in terms of b only, so we're going to rearrange this one. We're going to get that c is equal to 1 over b. And then substituting this into there, we'll get that a is equal to 1 over b e. Find the equation of the tangent and normal at the x-intercept of the inverse of f of x. Okay, so x-intercept of the inverse of f of x. So let's define. Oh my god, I'm not that excited. G of x is equal to 1 over b times ln of x on a. That, and finding the x-intercept is at x equals a, I think, because that's the x-intercept. Yeah, x equals a. So, and then we're going to go tangent line, g of x at x equals a. So we get tangent y is equal to 1 over a b x minus 1 over b, and then normal y is equal to negative abx plus a squared b. There we go. All right, find the value of a and b such that the gradient of the tangent at f of x is equal to the tangent at its inverse. Okay. So with this question, I think they made a mistake. Not too sure though, because essentially, as we found out, if a is equal to 1 over be, then the gradient of their tangents are the same, namely a gradient of 1. So there's actually infinite solutions of this, but I think they just failed to mention at what point they wanted the tangent to be at. And the second part of the statement is kind of redundant because the gradient of the tangent being equal to each other implies this anyway. So there's really no point of saying that. So yeah, this question is a bit bugged. Can't really solve it. Unless I'm tripping, you guys tell me in the comments. But yeah, moving on from that. A quadrilateral is formed by connecting a bunch of shit. All right. Okay. First of all, tangent to f of x at its y-intercept. So tangent to f of x at x equals 0. So that's going to be y equals abx plus a. And then this one was, as we calculated before, y equals negative 1 over abx plus a. And this one, calculated here, I think. Yeah, 1 over abx minus 1 over b. Y equals 1 over abx minus 1 over b. And then this one was, I think it was negative ab x plus a squared b. Yep. All right, so these four lines make a quadrilateral. So let's see what that looks like. Look at that. abx plus a, negative 1 over abx plus a, negative abx plus a squared b, and finally 1 over abx minus 1 over b. And let's zoom in. Ugh, that is, let's try and find a good value here. Square a equals 1. Yeah, that's a little more neat. A equals 1. Or 1.1. 1.1 is more accurate. This, and then the quadrilateral we want to find is the area of this quadrilateral here, as you can see. Looks kind of like a kite. Okay, so how we're going to solve this is, first of all, we're going to realize that the line y equals x cuts the quadrilateral in half. So we're going to find the area of this triangle, and then we're just going to multiply it by 2 to find the rest. Okay, so let's draw this out. Boom. Let's draw a quick kite. And then like that, I think. Yep. The line y equals x cuts through it. Okay, so now we need to find the relevant points. So we need to find this point, and this point. So this point here is the intersection of this red line here and this blue line here. So it's going to be the intersection between the two normals. So the intersection between this and this. So let's do that. Solve. Wait. Normal line GX. So this one equals to what? Am I tripping? No, a minus x over a times b. And we get this, a squared b over a plus ab plus 1. So a squared b over ab plus 1. This is 1. Sorry, no, this is a. Sorry, no, that's 0. The heck am I talking about? That's irrelevant. Anyway, this point is the x-intercept of this black tangent, which is the negative 1 over b, as we found in the triangle question. Yep, there. And then this point is the intersection of the two tangents. So intersection of this tangent and this tangent. So that's going to be solve a times b times x plus a equals to this. And we get a over 1 minus ab. Like that. All right, so to find the area, first of all, we're going to find the area above the x-axis, so this area here. And first of all, let's write the 2 down, because remember we have to multiply it by 2. So 2 multiplied by, first area is going to be the integral from -1 to b of 0 of this tangent here, which is abx plus a. And then plus the integral from 0 to a squared b over ab plus 1. So we're finding this area now of this normal, which is a minus x over ab. And then we have to consider this line y equals x as well, so minus x dx. So that's the positive area part. Now we have to find this negative area. And remember, since it's negative area, we have to minus it. So minus integral from a over 1 minus ab to -1 over b. Wait. So let me just put a bracket here. Minus of no, not 1 over b. Integral from a over integral from a over 1 minus ab to 0 of x dx minus integral from a over 1 minus ab to -1 over b multiplied by this, not multiplied by, of this tangent here, which is abx plus a. abx plus x. All right, and putting all that into the CAS, I'm actually just going to put it into my handheld CAS because it's just a bit faster. Just bear with me. Integral abx plus a plus a squared b over ab plus 1, 0, a minus x, minus integral a over a minus a over 1 minus b x minus integral a over 1 minus ab, and then abx plus a. Okay, and then that gives us an area of a squared plus 2 over b squared plus 1 over b squared ab minus 1 minus 1 over b squared ab plus 1. And there we go. All right. That is the end of the exam. I hope this was helpful. Good luck on your exam this Wednesday. And yeah, if you want me to do any other exams, please tell me in the comments. See you later.